In 6.1, we're going to be going over exponential functions. And to start off, we are going to look at exponential growth functions. So these are where we are growing by a percentage or repeatedly multiplying by some specific number, and that is how the situation is growing. So we have two different ways that we can write our exponential growth functions. This first one is using what we call the growth factor, which is when we know exactly what we are repeatedly multiplying by. And we write this as being A for the amount is equal to A0, which is our starting amount, multiplied by B, the growth factor, and then raised to the t power, where t is our time periods. So when it's exponential growth, that means that this b in the equation, the growth factor, has to be greater than 1. That means that we're multiplying by something greater than 1 repeatedly, so it's increasing in value, meaning it's growing. The A0, the 0 is just in the notation of this variable here, but this is our starting amount. And we can also think of this as the y-intercept of our function. The other way that we can write this is using our percent increase. And in this equation, we're given that the variable r. So we have A, the amount, is equal to A0, the starting amount, multiplied by 1 plus r raised to the t power. And with this, r is our percent increase. Specifically, it is in the decimal form. So if we have the percentage given to us in a percent, we need to divide by 100 to get rid of the percent symbol, because we don't want that in our equation. We want the decimal form of the percent increase. And another thing to note is our growth factor from the last formula B, that is equal to the 1 plus r, where they're the same thing. It's just two different ways of writing this, depending on whether we know the growth factor or if we have been given a percent increase to use. So now we're going to take a little bit of time to look at a situation here with bacteria to see how exponential growth behaves. So to start, we have, suppose you begin with 100 bacteria in a petri dish, and you know that the number of bacteria is doubling every hour. So let's fill out this table here. We have hours since beginning on the left column and number of bacteria on the right column. At 0 hours, there was 100 bacteria in that petri dish. 1 hour goes by, and we're now 1 hour since the beginning. Well, we've doubled it. We've taken 100 and multiplied that by 2, and that gives us 200. Another hour goes by. We've taken our original 100, we multiplied it by 2 for the first hour, and then we multiplied by 2 again because another hour had gone by when we're 2 hours past the beginning. So that gives 100 times 2 times 2, which gives us 400. Another hour goes by. We're at 3 hours. We have our previous of the 2 hours, 100 times 2 times 2, but now we need to multiply by 2 again because we're at 3 hours and we are at 800 bacteria. We continue this process. We're at 4 hours have gone by. Well, we're at 100, and then we need to multiply by 2 4 times from our starting amount to give us 1,600. And then lastly, we need to take this for 5 hours since the beginning, multiply by 2 an additional time, and we're going to get 3,200. let's take a look at the pattern that we have here with this. 1 hour that went by, I multiplied by 2 just one time. So we were getting a multiply by 2 to the technically first power. There was only 1 2 there. When 2 hours had gone by, I had multiplied by 2 2 times. So we multiplied by 2 to the second power, because that's 2 squared. With 3 hours, I had 3 sets of the 2's getting multiplied together. Well, that condenses down to being 2 to the third power. And what are these numbers corresponding with? Well, they're corresponding with our time period since the beginning, with how many hours have gone by since we had started. So our hours that have gone by, that is our exponent on this growth factor here. Our growth factor is 2 because that's what it means for it to double. But then we're raising it to how long it had taken. So now let's write an equation that will model this for our number of bacteria n as a function of the number of hours since observing the petri dish. So we have our number of bacteria. N is equal to, we started off with 100, and then we were multiplying this by 2 over and over again. So we're going to multiply this by 2, but now 2 needs to be raised to the power, and we're calling our power h here for our number of hours that have gone by. Let's also take a bit of time to graph this function to get an idea of what this looks like. So let's add some labels on this graph. We're going to have hours on our x-axis, the horizontal axis, and then we're going to need the number of bacteria on the y-axis. And to space this out a bit nicely, I'm going to go every 2 on the h-axis to be 1. So I'm going to have 1, 2, 3, 4, 5, 6, and 7. And then along the n-axis, I'm going to label every 2 lines to be 200 increase. So 200, 400. So now let's plot some points that we have from our table. We know when h was 0, our hours was 0, the number of bacteria was 100. So we can plot that on the graph. At 1 hour, we had 200. 2 hours, there was 400. 3 hours, there was 800. And then at 4 hours, we were at 1600. And that's going to be all that we're going to be able to fit on this graph here. So what we can do is try and connect these together. It's not going to be a straight line because exponential models are not linear. It's going to have a curve to it. And over on the left side, it's going to get closer and closer to the x-axis, or h-axis in this problem. And the one thing that exponential growth models always share is that the more we increase on the right side of our graph, the more steep it's getting. It's getting larger and larger for the y values, the farther we go to the right. Okay, so now let's use our model to predict the number of bacteria after 20 hours. Well, we have an equation, n equal to 100 times 2 to the h power. 20 hours is what we're going to need to replace h with. So n is equal to 100 times 2 to the 20th power. And now this we can put into our calculator to get the exact value. And you should then get 104,857,600 bacteria. So next, let's think about, suppose we need the model to tell us the number of bacteria B as a function of the days of the week since first observing the Petri dish. Rather than having it be in hours, we need it to be in days. Well, to start off, let's think about how many hours are in one day. Well, we have 24 hours in one day. So our 2 that we originally had in this, the 2 to the h power, I need 24 of those 2's in order for a full day to have gone by. So we're going to think of it, we have all our 2's multiplying together. I need 24 of these. So that's giving us 2 to the 24th power. So now when I have my equation, 100 times 2 to the h, my 2 to the h is going to be replaced with 2 to the 24th times my number of days that have gone by. And now this is equal to our function b here to tell us the number of bacteria as a function of days.